I wish everyone welcome to the seminar for finite geometries and groups. This talk is going to be in English because I've invited some people to attend online from various parts of the world. And I'm going to be talking about variations on the theme of higher dimensional designs. So by designs, I mean, first of all, Hadamard matrices. I'm going to be talking about them and some higher dimensional versions of Hadamard matrices. Symmetric block designs, this is going to be roughly half of the talk, and I'm going to just say a couple of words about mosaics of symmetric designs, about higher dimensional versions of them. But this is going to be probably the shortest part of the talk. The idea is first to give you a very brief survey of known results, to present alternative definitions, because for each of these objects you can generalize them to higher dimensions in several ways. So I'm going to talk about some alternative ways to generalize them to higher dimensions. And the focus is going to be on open problems and research directions. This year I'm on sabbatical. I'm going to next whole year have time to think about these problems, and I would be very glad if I could interest some of you to also sort of do some work about this. So let's start with Hadamard matrices. An ordinary two-dimensional Hadamard matrix is a square matrix, let's say of order V, with entries -1 and 1, such that this equation holds. What it means is if you multiply H by H transpose, you just get the identity matrix multiplied by the order. It basically means that the rows and the columns are orthogonal. So here are examples of order 1, 2, and 4, and here each two rows, the dot product is 0, and each two columns, as a consequence, is also these are not really what's usually meant by orthogonal matrices, because the rows are not normalized, but since they're all ones and -1s, the norm of each row is just the square root of V, and you can of course divide by square root of V, but the focus is going to be on the combinatorics. So essentially they're so scalar multiples of orthogonal matrices, but with these entries that are all the same except the plus or minus sign. They were actually not first studied by Hadamard, but Sylvester already wrote about them in the mid-19th century. I'm not going to read the title. At the time it was customary to have rather long titles. And well, he obviously defined them, and he had a construction for these matrices. If you look at this 4x4 example, you can notice that it's actually this 2x2 repeated 3 times here, and then here is just the opposite signs. So this is a Kronecker product of this small matrix with any Hadamard matrix, or here you get the recipe to build such matrices. Actually, you can take any two Hadamard matrices, do the Kronecker product, and it's going to preserve this property. And as a consequence, you can always construct such matrices for orders that are powers of 2. So for already Sylvester knew that they exist for all orders that are powers of 2. Hadamard wrote about them at the end of the 19th century, and he sort of came about because he studied this inequality. He proved an inequality for the determinant of a matrix. Well, of course, how large the determinant is depends on the entries, but if you bound the entries with, let's say, the absolute value of the entries is less or equal 1, then actually the matrices that attain this inequality are exactly Hadamard matrices. So they are kind of the matrices with the highest possible determinant under these conditions. And also Hadamard knew that they exist also, for example, for orders 12 and 20. So it's not just powers of 2. And he proved that if a Hadamard matrix for the V exists, then either V is 1, 2, or it must be then divisible by 4. So it cannot be any order, but the Hadamard conjecture, that's the first open
problem here is that they actually exist for all orders divisible by 4. So 12 is divisible by 4, 20. Of course, any power of 2 is divisible by 4. But it's tough to prove this. It's believed to be true widely, but there is presently no proof for this. Now, open questions are going to be in red. This is kind of more purple because this is a hard question. So people have been working on this for more than 100 years, and it seems that the proof is not so near. So this would not be a suggestion for research because it's a pretty hard question. There will be other questions. Now, the Hadamard conjecture was actually, he didn't write it out explicitly in this paper or in any other paper as far as I know. It was probably stated explicitly first by Paley, maybe earlier, but this is already in the 20th century. So Paley definitely thought that they could exist for all orders that are divisible by 4. And he had a construction from finite fields. So if you have a prime power, then you can, using the finite field of order Q, construct a Hadamard matrix of order if Q is 3 mod 4, then of order Q plus 1, because then Q plus 1 is divisible by 4. And then if it's not, if it has to be an odd prime power, I should say. If it's 1 mod 4, then there is a Hadamard matrix of order 2 times Q plus 1, which is then divisible by 4. That's a very old construction, so from the first half of the 20th century. It covers an infinite number of orders, but of course not everything. So, for example, the smallest order for which a Hadamard matrix is currently unknown is 668, which is 4 times 167. And of course, if you look at Q either V minus 1, it's not a prime power, it's a product of 23 and 29. And even for this second type of Paley construction, V over 2 minus 1 is again 3 times 37, so it's not prime. This construction does not work. There are a lot of other constructions, but this particular order is not covered by any. So this is currently the smallest unknown order for a Hadamard matrix. Recently, there was a conference in Sevilla. Ilias Kotsireas talked about the Hadamard conjecture, 130 plus years of the Hadamard conjecture, and he gave a very nice account of various types of construction. I'm not going to talk about this much because I want to focus on higher dimensional versions of Hadamard matrices. One point at which they were generalized to higher dimensions is, well, Paul Schlichter is a physicist. He wrote a paper in 1971 about 3 and 4 dimensional Hadamard matrices, which was not very noticed by the mathematical community because it was in the Bulletin of the American Physical Society. But then at the end of the 70s, he wrote another paper in the IEEE Transactions of Information Theory, and that was well noted. And then people really started studying them in the 80s, let's say, people from Australia, from China, Jennifer Seabury and others. So what was Schlichter's definition for n-dimensional Hadamard matrix? First of all, an n-dimensional matrix with, let's say, minus 1 entries is just a function from 1 to v to the nth power. This is a Cartesian product, so it's a function of n variables, which takes values in minus 1, 1. You can think of it as an n-dimensional array, a square array, let's say, v times v times v, so on, n times. N is always going to be the dimension. So v is therefore the order. I chose another letter. And when is it Hadamard? Well, one way Schlichter said this could be done is if all n minus 1 dimensional parallel slices are orthogonal. So if it's a 2-dimensional matrix, if n is 2, this is just the condition that the rows and the columns are orthogonal. So these are the n minus 1 dimensional slices are just rows and columns. If it's an n-dimensional matrix, you have, well, how do you get these slices? You fix one coordinate and you fix it here to another value, and then you vary over all other coordinates, and you do this scalar product, sum of the products, And if A is equal to B, then it's going to be just V to the power of n minus 1, because then you're squaring the minus 1s and 1s. You're just taking a sum of 1s. However, if A is different from B, then it has to be 0. This is the Kronecker delta function. So this is what is meant by orthogonality of n minus 1 dimensional parallel slices. There is another definition, also in his paper. A proper Hadamard matrix is such a function that whenever you take a two-dimensional slice, so you fix all coordinates except 2, so you get an ordinary two-dimensional matrix, it has to be Hadamard. So all of these two-dimensional slices in all directions have to be Hadamard matrices. Actually, this is a stronger definition. So whenever this is satisfied, then it is Hadamard. I'm going to talk about proper Hadamard matrices and ordinary, let's say, n-dimensional Hadamard matrices. For n2, it's the same. So, but for dimensions from 3 above, this is stronger. This is really a weaker definition than this. And there are already also by Schlichter, actually there are also in between orthogonality conditions you can impose on these matrices. Here's just the definition of what are k-dimensional parallel slices. And then he defined the degree of propriety of an n-dimensional matrix as the least d, such that all parallel d minus 1 dimensional slices are orthogonal. Now, if this holds for, let's say, 5-dimensional slices, then it also holds for 6, 7, and so on. So it holds for all k greater than equal d. And ordinary n-dimensional Hadamard matrices are just of orthogonal of degree n, whereas proper are degree is 2. So a degree 2 matrix is automatically degree 3, 4, and so on. And basically, I'm just going to be talking about these two extremal cases. Although there are a lot of in-between conditions, they have mostly been studied either for degree 2 or degree n. So the strongest possible or the weakest possible. Schlichter also proved that, well, if you have a proper n-dimensional Hadamard matrix and you take a slice, it's going to be an ordinary Hadamard matrix, dimension 2. And then, of course, the order must be 1, 2, or divisible by 4. However, for an ordinary n-dimensional matrix of dimension at least 3, you cannot prove that the order has to be divisible by 4. You can just prove that it's either 1 or even. And I will show you examples where it really isn't divisible by 4. So they could exist also, let's say, for order 6 from dimensions 3 up. Another thing Schlichter had is a construction. It's basically the same as Sylvester's Kronecker product construction. Whenever the order is a power of 2, then there exist these stronger proper n-dimensional Hadamard matrices for all dimensions. So this is what Schlichter already knew. And then the most important step for these proper n-dimensional matrices were by a Chinese mathematician, Yi Shan Yang, if it's pronounced, I think, in the mid-80s, and also Auric Delaunay in his PhD thesis about the same time proved this theorem I'm going to call the product construction. So whenever you have an ordinary or two-dimensional Hadamard matrix, then you can build an n-dimensional Hadamard matrix of the same order for all dimensions. So it's just a formula that gives you, so how do you build this n-dimensional thing from the smaller, from the ordinary, so the two-dimensional matrix, and it works, yeah. And basically, it's kind of killed the topic, because now the spectrum of all orders for which Hadamard matrices exist, at least for these proper n-dimensional matrices, is the same for all dimensions n. So it doesn't, there's no point in studying the higher dimensional ones if you're just in existence, and the orders are going to be the same because of this product construction. Of course, you can ask other questions. Deloni, with co-authors, has quite a few other papers about automorphisms of them and others. And here's the question, for example, well, the green questions are going to be the one I know the answer. So you can ask, are there any examples with inequivalent two-dimensional slices? Because the way this construction is proved, so how do you know that any slice is a Hadamard matrix? Because it's equivalent to the original one you started with. Equivalence means you're allowed to permute the rows and the columns, and you're allowed to multiply the rows and the columns, individual ones, by to change the signs, to multiply them by -1. So actually here any slice is equivalent to this matrix you started from. Are there any examples, and another known construction have also the same properties? One and the same matrix or equivalent one all over in this big n-dimensional matrix. So you can ask, are there any examples that have inequivalent two-dimensional slices? And the answer is going to be yes. I'm going to show you examples later. Okay. Yeah, we could try. So maybe it will be better. The visibility should be better if we turn down the light. Is it better now for the ones who are looking online?
Yes, it's better.
Okay, thanks. So ordinary n-dimensional matrices, the ones that are not proper, are actually more interesting because they can exist for orders that are not divisible by 4. Here's an example of a 6 times 6 times 6 three-dimensional Hadamard matrix from different angles. Now, if you take a slice, it's not going to be Hadamard. It's a 6 times 6 matrix, Hadamard matrices of order 6 do not exist, but any two slices in any direction, parallel ones, are going to be orthogonal, so this is an ordinary three-dimensional Hadamard matrix of order 6. And they were studied a lot by Yishan Yang and some co-authors. He has a book, Theory and Applications of Higher Dimensional Hadamard Matrices. I'm just going to briefly mention two constructions of his. If you're just interested in ordinary n-dimensional Hadamard matrices, there is a construction that can increase the dimension. So whenever you have an n-dimensional Hadamard matrix of order V, then you can just, by adding a coordinate, very simple, build an n+1 dimensional one. So again, if you have a two-dimensional matrix, you can build up the dimension as how much you like. But the problem is you're not going to be able to construct the ones that are the order is 2 mod 4, because of course there are no examples for n2. So you have to kind of start from a higher dimension if you want these orders that are 2 mod 4. There's another construction, well, this is my name digit construction, where he takes a two-dimensional Hadamard matrix and he folds it up into higher dimensions. So it has to be of a specific order. And what you do is you just interpret these indices as digits in base 2t here, and that's why I call it digit construction. In this way, you can always sort of raise the dimension. Here you have dimension 2, and here the dimension is raised to 2 times s. And the order is kind of lowered because you're kind of picking up these pieces of this large two-dimensional matrix and building a higher dimensional one. The problem is, however, that the dimension is always going to be even, so you're not going to be able, say, construct examples of dimension 3. As a consequence of these two theorems, from dimension 4 up, again, if the Hadamard conjecture is true, then these n-dimensional Hadamard matrices actually exist for all even orders. If you have two-dimensional matrices of any order divisible by 4, then you can build all even orders, but just from dimension 4 up. And what about dimension 3? So this is kind of more difficult question. If you have dimension 3, then you can just increase the dimension from there, but you cannot build them, well, in some cases you can build them directly. Young has this theorem which covers orders of the form 2 times 3 to some power. So let's say 6, 18, 54. But there are a lot of, this is quite sparse. There are a lot of orders for which he didn't know whether ordinary n-dimensional Hadamard matrices exist. 10, 14, 22, these are all congruent to 2 mod, so oddly even, divisible by 2 but not by 4, for which he didn't know. So he asked in his book whether they exist for other orders that are 2 mod 4 and not of this form 2 times 3 to something, and to try to construct more such examples. Now the question is green because we managed to answer that, and already in Schlichter's paper he's kind of suggested, why don't you take some known algebraic constructions of ordinary for 2-dimensional Hadamard matrices and try to generalize them to higher dimensions. And basically this is what we did in this paper with Mario Papčević and Christian. This is kind of a generalization of this Paley's constructions from finite fields. Here's just a huge formula which will give you, for any odd prime power, which will give you a 3-dimensional, so you have 3 coordinates, Hadamard matrix of order q plus 1. For example, if you take q9, then you will get an ordinary 3-dimensional Hadamard matrix of order 10. Here's from some other viewpoints. And this first picture, how did we get this huge formula? Well, we constructed some examples. We found this by computer, and here you can see that it's the symmetry, what's acting on this 3-dimensional Hadamard matrix is actually the PSL group, and then it wasn't so difficult to figure out that you had to use index the thing by a projective line, basically just a finite field and infinity, and we kind of got the formula from there. And now our construction actually works when Q is either 3 or 1 mod 4. For 3, it will give you a proper Hadamard matrix. So all of the slices are going to be Hadamard matrices. And for Q1 mod 4, it will give you an ordinary, so only the n-1 or 2-dimensional slices are going to be orthogonal. They're not going to be Hadamard matrices, obviously, because the order is then 2 mod 4 of the matrix. Now, we all know that they exist for 10, 14, 26, 30, and so on, for all of these orders that were previously they were open. But still, there are infinitely many that are not covered by this construction. This is just this first algebraic construction already from the first half of by Paley, generalized to dimension 3. So these are all orders, as far as I know, for which the question is still open. Are there any ordinary 3-dimensional Hadamard matrices of order 22? We tried a little bit for 22, but didn't succeed. But for all of the others, we didn't even try. So maybe this wouldn't be such a bad question to try to answer. I think that the constructions, you probably could make some also other known constructions that work for 2-dimensional matrices and try to generalize them to higher dimensions, like we did here for the Paley type construction. Another question could be even for dimension, so basically this is for dimension 3 and here also, but for other even dimensions it's kind of settled, but just modulo the Hadamard conjecture. So if we know that the Hadamard matrices, the 2-dimensional ones, exist for all orders that are divisible by 4, then we can construct these higher dimensional ones for all even orders. However, I think that actually probably the question is easier for ordinary n-dimensional Hadamard matrices, maybe of order for dimension 4. So maybe you can prove this existence for even orders without using the Hadamard conjecture, because that's how Young did it. Maybe this would also be a good question to try to tackle. Okay, here is this Codesco conference in Sevilla, the group photo. I'm right here, and behind me is Ilias Kotsireas, who gave the talk about the Hadamard conjecture. And of course, I asked him whether he knew anything about higher dimensions. This wasn't in his talk. And he pointed to this guy, Edina Grang, who, together with some co-authors, has a different definition of n-dimensional Hadamard matrices, as it turned out. So his definition of higher dimensional Hadamard matrices is based on this so-called Bhattacharya-Messner product for, he called them hypermatrices. This kind of product was defined by Dale Messner and Bhattacharya, who were actually trying to generalize association schemes to higher dimensions, basically for dimension 3. And then they defined this way, how do you multiply three-dimensional matrices? And here's their definition. So the product of, let's say, three-dimensional matrices, they're all of the same order. This is not necessary. You can also do it for some non-square matrices, but I'm going to assume that they're all of the same order to make it easier. The product is a ternary operation. So normally if you have two matrices, you have two matrices, multiply them, get a third matrix. Here you have to take three-dimensional matrices. The product is completely analogous to what we would do in 2 dimensions. So you take a kind of column, a row, and a column in the third direction. You just sum from J1 to V. Here it's in the middle, here is the last, here is the first index. And then you do this product of the rows, columns, and the third columns, and sum it up. So this is practically what you would, if I told you, generalize it to product to higher dimensions, this is what you would do. You can do it, of course, for 4-dimensional matrices, but now it's a quaternary operation, so you need 4 matrices to multiply them together in this way. To define Hadamard matrices, I need some more definitions for these higher dimensional matrices, or hypermatrices, as Dina calls them. So first of all, the transpose of a matrix. Well, the transpose just exchanges the indices, the order of the arguments. If you have just 2, then there's only one way you can do it. Of course, if you have n indices, you can permute them in various different ways, but a transposition is going to be just a shift to the left. So cyclic shift of the coordinates here is from 1 to n, and here it starts with n, and actually it's to the right then. Yeah, cyclic shift to the right. This has the advantage that it's an operation of order n. So if you do it n times, you're going to get back the same matrix. And also it behaves well with respect to this product. You just have to also shift these factors to the left, and then it works. So if you do transpose of the product, it's just the product of the transposes in this order. Here is kind of what you would maybe call an identity matrix. So it's just a higher dimensional Kronecker symbol. 1 if all of the arguments are the same, and 0 otherwise. 1 on the diagonal and 0 everywhere else. But this is actually not an identity element for this Bm product, but it's related. So you can do for n3, you can do this I matrix as a product of J is just all ones matrix with this delta, and then it works. So if you put A here and I and the transpose of I here, it's going to give you back the same matrix. So here is a definition of Edina of Hadamard matrices of dimension n. So this is kind of the generalization of what we had in the beginning. Just we had like H times H transpose has to be the identity matrix. Here you have n factors because it's an n-dimensional matrix, and H and its transposes because there are n of them, right? And this product has to be this Kronecker delta. So This is his definition. Now, the smallest example, 2 by 2, here's an example for Schlichter's definition, for the first definition I gave you. So the filled cubes are -1s, the empty cubes are 1s. I should have said that when I showed you the 6 times 6 times 6 example. So you have just 2 -1s on the diagonal and it works. However, for the second definition, alternative definition, this would not be an example. You would have to put a single -1 and then all of the other ones would have to be 1s. This picture is perhaps misleading because it actually matters where you put this -1. So the definition of a three-dimensional 2 by 2 Hadamard matrix, it's a function that takes these triples and maps them onto either 1 or -1. So if you want one -1 sign and all of the other ones, you have 8 possible places where you put them. And it matters whether it is Hadamard or not. So for this column, it's not the Hadamard matrix. Here it is, and here it is. This is what I really don't like about the definition, because it's not invariant under symmetries of the cube. So here you can kind of rotate it and, I don't know, take symmetries in all ways possible. It's invariant, but this is not invariant. So you can kind of take this -1, transfer it to another place, and it's not going to be Hadamard anymore. But the good thing is there are a lot of unknown questions. So, for example, for this smallest possible non-trivial order of 2, what they proved, Edina and his co-author Yuval Filmus, is that they exist, of course, for n2, because for dimension 2 is just the same, all the same Hadamard matrices. But they don't exist for other than 2 for even dimensions. So there is no 2 times 2 times 2 times 2 4-dimensional Hadamard matrix according to this definition. They do exist for order 2 for odd dimensions, 3, 5, and so on. So this is kind of weird. They don't exist for all dimensions. We had like for all possible dimensions. And well, this non-existence in their paper, they prove is just for order 2. So a natural question would be, do they even exist, let's say, for dimension 4 and order a little bit bigger? Let's say, take order 4. Whether 4 times 4 times 4 times 4 matrix satisfying this equation exists or not, it seems like a silly small question, but if you look at it, so now if you're doing it the crudest possible way, just checking all possibilities, how many are there? You have like 4 to the power 4 positions in this matrix, and in each one of them you can put either 1 or -1, so it's already 2 to the power 256, which is 10 to the power 77. So you're not going to be just able to just check all of them, but I think for 4 times 4 times 4 it should be possible to calculate. So maybe not in this crude way, with a little bit of effort, you can probably answer this question. And my guess would be that they actually, for even dimensions bigger than 2, they don't exist at all. And now the other thing they proved in their paper is that for odd dimensions and for orders that are powers of 2, they do exist. So this is just the same as Sylvester's construction unit. We have an n-dimensional version of the Kronecker product and it works, but they don't have a, let's say a question would be, for odd dimensions, does the order have to be divisible by 4? There is no, even no claim in their paper, so this would be a natural question. And are there any examples where the order is not a power of 2? This is the next natural question. So one construction that works nicely for this definition is the Kronecker product, but can you also do analogous constructions for other known constructions for Hadamard matrices. So, for example, is there a Paley type construction for these type of matrices? I don't know. These are all open questions. I haven't had much time to think about it because I've only learned about this definition recently. But I think they're probably good questions. So maybe if there should be, well, there should be some easy ones, and maybe a good place to talk about this would be the next conference in Sevilla, which is going to be May next year. It's going to be the workshop on, well, main topic is Hadamard matrices. So this is one conference that would be perhaps suitable. Another one is the 5th Pythagorean conference in Kalamata. Ilias is one of the organizers. Alfred is another one. So this is another place where such talk would be good if anyone manages to solve some of these questions. Now, Hadamard matrices are done. Now I'm going to try to say something about symmetric designs. So, symmetric designs, here the definition is just that it's a matrix. It's a V times V matrix, this time not with -1, 1 entries, but with 0, 1 entries, such that this equation has to hold. If it holds, then it is a VK lambda design. The customary, the order of the matrix is not V, but K minus lambda. This is in design theory. And the customary, well, is usually the letter is n, but n is going to be the dimension for this talk, so I'm going to write m for the order. Now, here's the smallest non-trivial example, a 731 design. Of course, it's just incidence matrix of the Fano plane, of the projective plane of order 2. I'm going to talk about them as matrices because this is the way they're generalized to higher dimensions. Like for Hadamard matrices, the necessary condition was that the order had to be divisible by 4. Here you have actually 3 parameters, but they're not independent, so this equation has to be fulfilled if they exist, these symmetric designs. The question whether for a given triple of parameter, whether they exist or not, is much more difficult than for Hadamard matrices, because the existence of Hadamard matrices is just a special case. So from a Hadamard matrix of order 4 m, you can build a symmetric design for these parameters. If you knew about symmetric designs, you will be able to answer the question for Hadamard matrices too. And of course, there are other symmetric designs. Projective planes are symmetric designs with these parameters, and it's a very difficult question whether there are any for non-prime power orders. So this is not, let's say, very good topic for a PhD thesis because it's too difficult. Okay. A good way to construct these objects are so-called difference sets. If you have a group of order V, a difference set with these parameters is just a K subset such that the differences I'm going to be using multiplicative notation here, so the differences are kind of x to the power -1 times y, that they cover the whole group evenly, so exactly each element except the neutral one is covered exactly lambda times. If you have such a subset, then you can build a matrix with, according to my definition, a symmetric design. It's a very simple construction and very well known. And of course, this has some additional property. It has G as a regular automorphism group. So you're not going to be able to construct every symmetric design in this way. For example, the 731, of course you can, but for parameters 25, 9, 3, these designs are known to exist, but there are no 25, 9, 3 different sets in any group. So this is kind of a restriction, but it's still a good way, an easy way to get symmetric designs. And here in this paper, which is going to appear in Ars Mathematica Contemporanea, we kind of studied an n-dimensional version of these symmetric designs, which are now just n-dimensional V times V times V, so n times matrices with 0, 1 entries, such that their two-dimensional slices are symmetric VK lambda designs or incidence matrices of them. So it's just like or the stronger, the proper Hadamard matrices, but for symmetric designs. Of course, we are not the first to define such objects. Warwick Deloney already in 1990 had a paper where he defined much more general class of n-dimensional designs, which includes Hadamard matrices, symmetric designs, I don't know, orthogonal designs and other stuff. He calls these proper n-dimensional transposable designs, and these, we call them cubes of symmetric designs. This is just a special case of his definition. He also had a book with Dane Flannery, in which, well, among other things, studies these n-dimensional designs of various sorts. And this is already a known construction, but an important one. Whenever you have a difference set, so if you have this nice small object, a k-dimensional, subset of a group of order V of size k with this property, you can actually build an n-dimensional cube of symmetric designs for any dimension. From the difference set for the Fano plane 0, 1, 3 in group of order 7, you can also build not just the Fano plane but also a cube of Fano planes. Or so this is sort of now the filled cubes are ones, the empty ones are zeros, and whenever you take a slice, any slice you want, two-dimensional, it's going to be an incidence matrix of the Fano plane. Natural question is, are there any examples not coming from this construction? We call these difference cubes that are from different sets. In dimension 2 there are, but are there any in higher dimensions? So are there any non-difference cubes which are actually not equivalent to a cube obtained from a different set? Related question, are there cubes with inequivalent two-dimensional slices? This is kind of related, because if there was such a cube that you take two different slices and you're getting non-isomorphic symmetric designs, it wouldn't be able, this construction covers all of the slices are the same design, the one obtained from this development from these different sets. So if you had such an example, it would have to be a non-difference cube. And we answered these questions in our paper. We have a slight generalization of the construction from difference sets. Now you need a design, so V blocks, which are different sets, and they form a symmetric design. Then you can also make such a thing. The usual way, how do you build a design, now looked as an incidence structure, with blocks that are different sets? You just do the development. So you take a different set and take all of its translates in this group, and it's going to be symmetric designs with these parameters. And if you do it starting from this, you're just getting a difference cube. It's the same construction if this is a development of one of its blocks. However, you can also do it in, well, not in the cyclic group, but there is another group. This was for order 4, so it's a cube of projective planes of order 4 or 25, 5, 1 designs. There is also a non-abelian group of order 21. And there are even more inequivalent different sets with these parameters. And you can build a block design from these blocks, which is not the development of its blocks. And if you do that, you're also going to get a cube of these projective planes of order 4, but it's, as you can see, not so structured anymore. So this is an example. However, this does not answer the question whether there are any examples with inequivalent slices, because there is only one projective plane of order 4, so you have to take some other parameters to be able to do this. And for this, well, it's an infinite family of parameters, we can do this. The smallest one is for M2, 16, 6, 2. You have 3 non-isomorphic designs. I'm going to call them the red, the green, and the blue design. And you can, if you take all 3 of them, you can get from different sets. this red one you can get from a different set in elementary abelian group of order 16. If you take development of one of these different sets, you're going to get a cube that is red all over. So all of the slices are the red design. You can also do it for the green design in another group, in this group. And for the blue design in a non-abelian group, you can do it from a different set. However, in this elementary abelian group, there are so many different sets for the red designs that you actually can build the green designs from these blocks. And then you're going to get a cube which has like red slices in one direction and green slices in two other directions. And it's obviously not a difference cube because a difference cube would be the same color all over. You can also do it for the blue design, and this is also possible. So in this group, there are both different sets that give you the red design and ones that give you the green design. And you can build using these different sets the blue design. You're going to get an example with slices of all three colors here. And also this is possible. So this is also all a special the consequence of this group cube construction of ours. The question was whether there are any cubes that do not come from our construction, more general one. And the answer was also yes. We could find examples which had slices with different colors from in all directions. This could not be a group cube because then it would be all of the same in two directions. Only one could be different color. So this is an example for, well, also this is possible for, just for these parameters, 16, 6, 2, we do have all kinds of examples. Actually, there are exactly 27 difference cubes, then 946 more non-difference cubes, but group cubes. And then there are, the majority of them are actually non-group cubes. More than half of them come from, do not come from our construction. But this is the only example we have, 1662 for non-group cubes. These parameters are so-called Menon type symmetric designs, which means that they can be transformed to Hadamard matrices. And if you do it for these examples I showed you, you are going to get n-dimensional Hadamard matrices with inequivalent slices, which is up to now, as far as we know, no other construction can do that. So this one gives you such examples. Now, open questions. The most annoying parameters are 25, 9, 3. Because there are no different sets there, you cannot use our construction, and we don't know whether there are any designs. Of course, there are designs, but are there any cubes of dimension 3 or more? Actually, we don't have any non-group cubes. For group cubes, you do need groups and different sets. Except for these parameters, we don't have any examples. A frustrating one is 1573, which is smaller. You should be able to do it there by computer, but we didn't manage to find any. So this is the only example where we do have non-group cubes for these parameters. The most obvious question would be, is there a product construction for cubes of symmetric designs, as there is for proper Hadamard matrices? I don't know. So this is, I tried, it might be obvious, maybe I'm missing something obvious, but I don't know. So if there was such a construction, you could just take the two-dimensional 2593, one of them, and do a higher dimensional version of it. But I don't know how to do it. Well, for the product construction for Hadamard matrices, you're multiplying ones and minus ones. Here you're multiplying zeros and ones, and then the zero kind of swallows everything. It doesn't work that way. And I don't know how to do it in any other way by replacing zeros with minus ones and doing a different kind of product. Maybe it's possible, but as far as I know, the question is open. And then there's this question whether there are any Hadamard matrices with inequivalent slices, except the ones I showed you, because the Menon designs actually have to be of square order. Are there any examples with inequivalent slices but non-square orders, let's say for Hadamard matrices? This is another one. We tried but didn't manage to find. Now, I have some more time. I'm going to talk about well, first I have to tell you something about room squares. Room squares, another completely different type of combinatorial object. They're called, they're named after Thomas Gerald Room, an Australian mathematician again. He defined them in 1955. Now here's the definition. So it's not really related to the stuff I talked about so far, but I have to, just to give you an idea of another generalization of squares of these symmetric designs, I have to define it a little bit. It's a V times V matrix again. These times some of the entries might be empty, and the ones that are not empty are just filled with two subset of this set, infinity and 1 to V. So it's actually a V times V matrix, but with elements from a V plus 1 set of this size. And there has to be regularities. I'm not going to read them because it's not really important. And here's an example of such an object of size 7, of order 7. So, okay, it's quite a nice object. And also it's equivalent to a lot of different other combinatorial stuff. For example, a room square of order V is equivalent to a pair of orthogonal 1 factorization of the complete graph. I'm just going to show you pictures. So from the rows of this square you get 1 factorization, from the columns you get another, and they're going to be orthogonal. And also a room square of order V is equivalent to a pair of orthogonal symmetric Latin squares. Again, you can define using this room square one matrix using the rows, that's the red one, the other one using the columns, the blue one. They are Latin squares and they are symmetric. So as they are symmetric, they can't really be orthogonal. If you have one pair appearing above the diagonal when you superimpose them, it's going to appear twice because it's also appearing below the diagonal. But apart from that, so it's as orthogonal as symmetric Latin square can get. So this is orthogonal symmetric. This is what is meant by orthogonal symmetric Latin squares. As far as existence of room squares, this is basically a solved problem. So room squares exist only if the order is odd and it's not 3 or 5. For all other odd orders, they do exist. It took some time to prove it from the definition, while the proof was completed in 1973, and it was a success of design theory. It required some pretty ingenious techniques, so some recursive constructions, and then there were these missing cases that had to be computer constructed and so on. But the consequence is actually room squares are not studied so much anymore, because I think it's because the existence question is completely settled, so no one cares anymore. There are no conferences so exclusively devoted to room squares, but there are some open questions other than this spectrum question. For example, there is an obvious n-dimensional generalization of room squares. It's called room cubes, and the definition is the following. So you have an n-dimensional matrix of order V with entries from the same set, so the same type of entries, either empty or two subsets. But now what you're asking for is that every two-dimensional projection is a room square. Not a slice, but a projection onto two coordinates. So here's a three-dimensional cube. If you look at it from the front, let's say, you're going to see a room square. And if you look at it from top, you're also going to see a room square, and also from the side view, it also gives you a room square. This is the kind of object which is called a room cube. So it's quite different from what we had so far. So far we took slices and we asked that the slices are the two-dimensional objects. Here you're doing projections. The question would be, why are you doing it now this way? Well, because it generalizes nicely to the equivalent objects. A two-dimensional room cube or a room square was equivalent to two orthogonal 1 factorizations of the complete graph. Now an n-dimensional one is equivalent to n mutual orthogonal these factorizations. It also works out for the orthogonal symmetric Latin squares. And now there's a weird thing. The dimension is for these room cubes is actually bounded by the size, by the order. Let this mu of v be the largest possible dimension of a room cube of order v. Then it's known that mu of v is less or equal v minus 2. So the dimension cannot be as large or it cannot be bigger than the order of this cube. For we didn't have any such restrictions for either cubes of symmetric designs or Hadamard matrices. This is completely well, it's not so weird because there you have like almost like orthogonal Latin squares, and you cannot have infinitely many orthogonal Latin squares. It's a well-known fact. So this is why the dimension is bounded by the order. Actually, conjecture by Walter Wallis is that this bound is not sharp, that there is a much tighter bound, so half of this square, roughly. I don't know, I didn't color this conjecture because I don't know how difficult this is. It might be doable, but I don't really have as much experience with rooms cubes, so I don't know. Now, we could do the same type of thing with symmetric designs. We could say, let's not look at the slices, let's look at the projections. If you take a Fano cube and do the projections, you're going to get matrices filled with ones, because in every row, column, or the third direction, there are 3 ones. So if you project, you're just going to see ones. So you have to do a slightly less crowded matrix with less ones, and you can actually do it. So this is a type of object of this room cube type. So you have less ones here, and if you look at it from the 3 possible directions, you're going to see incidence matrices of Fano planes. You can do it in 2 non-isomorphic ways, and here you can actually put more incidences without changing. For the first one you couldn't, but for the second one you can put more ones without changing the 3 projections. So what is a projection? It's well, this is already the definition of a projection cube. This is what we want. It's just an n-dimensional matrix of zeros and ones of order V, such that every 2-dimensional projection is a symmetric VK lambda design. But what is a projection? It's a sum where you fix 2 coordinates, let's say the first 2 coordinates here. So it's projection coordinates 1 and 2. And then it's an ordinary 2-dimensional matrix where you keep these entries and you sum over all of the other ones, of all other indices. So if you take the sum, the usual sum over the integers or over the real numbers of any other normal field of characteristic 0, then if you want that these projections are 0-1 matrices, you at most 1 entry 1 can appear for each choice of x and y. So the total number of ones in this whole cube is going to be v times k, the number of incidences in a VK lambda design. However, you can also do the sum. If you're really looking at like a shadow, you're actually, if you see 2 ones, it's still going to be a 1. This is, if you take the sum in the binary semi-field where 1 plus 1 is just 1, then you can make more examples, and because now this would also be then this with twice as many incidences as this would be an example, and you could just pick any one of these added ones and either put it there or not. So it would give you a lot of examples, 2 to the power 21, and it's a mess really. And you could also work over the binary field. But then you would get even more examples because you just could change zeros and 1 as long as you do this an even number of times in any row or column. It's not going to change the sum over Z2 or F2. So I think the correct definition is over Z. We just want these cubes with the least possible number of incidences, which is V times K, and we're not doing sums either in this semi-field or in some other field of non-zero characteristic. First question, are there any cubes of dimension greater than 3? I showed you one example of the Fano cube of dimension 3. So here's just an incidence matrix of a Fano plane, or we could call it a projection cube of dimension 2. And you can sort of model it with these incidences. You record where are the ones. The ones is here in this position, 1, 1, 1, 2, 1, 4, and so on. So for the three-dimensional Fano cube, you are adding one coordinate to the incidences. For the four-dimensional, I cannot show you a picture, but I can still do this. I can keep adding coordinates until dimension 7. Now, after 7, I don't know. But there are definitely higher dimensional objects. And this is kind of a representation of this cube. It's similar to what we called an orthogonal array, but the definition is a little bit, well, it is an orthogonal array of strength 1 and index, well, in general, it would be K, because you have in each column, if you look at these entries, the columns of these n tuples, each symbol appears K times. The symbols are from 1 to V. But there is another condition it has to satisfy. Each two columns, if you take any two columns and look at these pairs, they have to be incidences of a symmetric design. Are there other combinatorial objects you can model this with or equivalent to this? So either you can look at it as a cube or this type of thing. And well, you can ask whether there are any examples not with these smallest possible parameters. Let's again say that mu of Vk lambda is a larger possible dimension of a projection cube with these parameters. I have some computational results. So for example, for this smallest, it's rather trivial, 3 to 1, it's exactly 5. For the other ones, I just have examples. I already showed you that I can do this for Fano cubes up until dimension 7. For this, I can do it to 11. Well, it seems like it's always V, but I don't know here. Perhaps here the search was not so exhaustive, so it could be higher, but this is how big examples I do have. For example, for these are projective planes of order 5. I can do it up to 6. Probably they exist for larger ones too. But the obvious question is there an upper bound on this, as there is for room cubes? I think yes, but I have a very poor candidate for now. It's quadratic in V, not linear as for room cubes. So I'm not going to speculate, but this I think is a nice question for which I don't have any answer right now, but I think it should be doable. Is there a different set construction? Well, obviously I got all of these examples from a different set type of construction, but I'm still working on the precise definition. What would be a different set for this type of n-dimensional cubes? And you can ask other questions. Well, some of them I know the answer. Are there any projection cubes with inequivalent projections? I have an example, of course, for 16.6.2, where in two directions you get the red design, in the third you get the green one, or you can also do an example like this. And I can also do red and the blue, because there are groups which allow for both types of different sets. I do not have an example where all three colors appear in. So this is something, I think it probably is possible, because not by a different construction, but some other means. You can probably do such a projection cube where in the three direction you will get three non-isomorphic designs. Now, this is kind of, I think, a good research direction. Maybe these projection cubes of symmetric designs, which as far as I know are completely new, there are a lot of questions that could be asked and answered also. Now, just the last couple of minutes, I'm not even going to define what are mosaics of combinatorial designs. They were defined by Oliver Mielke, Markus Greferath, and Mario Pavčević in 2018. I'm just going to give you an example from this paper that was recently accepted in examples and counterexamples. So this is a mosaic of projective planes of order 3. It's a matrix filled with incidences. All of the colors represent incidences for a projective plane of order 3. This is quite an untypical example because it's not made from a different set. All of the other examples I have come from, at least for projective planes, come from different sets. You have to tile the whole group by disjoint different sets. This was studied even earlier by Ante Čustić, Yu Zhu, and myself. And there is a very nice interpretation. You can think about these tilings of groups with different sets as, at least in the cyclic case, as necklaces with very regular properties. I'm not going to talk about now. And how do you make a mosaic from it? Well, you just cut it, straighten it out, and do, for the cyclic group, you just do shifts. And this is going to be a mosaic of projective planes of order 5. Now, perhaps a silly question, is there a higher dimensional version of this? Now, it reminded me of two classic films. One is Jaws. Obviously, this is a very famous film about the attack of the great white shark. And there's another famous disaster movie about Twister, about tornadoes. Now, there was a film where I think that the line of thinking was, we should take both of these ideas and put them in one film, and then what you get is Sharknado. It's a rather silly film. But, well, the poster says it all, enough said. It's a tornado which picks up some sharks from the sea, and then these sharks fly around and attack people. The movie does not have any problems with the laws of physics, but it's, well, I actually watched it in order to prepare for this seminar. And you know, there are these movies that are so bad that are actually good. This one was kind of made with this premise, but it doesn't really work if you're doing it on purpose. You have to do it like, really, you think about doing a great movie, but they were kind of cynical about it. There is a review that said, if you watch these movies, it lasts about an hour and a half, these are 90 minutes of your life you're not going to get back, but you will not want to get them back anyway. Maybe, okay, I could watch it for an hour and a half without falling asleep, but it's not that funny. The poster says it all. Anyway, now we have two ideas to combine symmetric designs. One is you make mosaics. This is a mosaic of projective planes of order 5. And it was made from different sets. But from a different set, you can also make a cube of projective plane of order 5. Now you can combine this, and you can make such a colorful cube, which is completely filled with colors, in such a way that whenever you take a slice in any direction, you are going to get a mosaic of these projective planes. I don't even know how to call this. Maybe cubes of mosaics of designs, or Sharknado designs would be a good maybe name for this. But I don't think this is a very prospective research direction, because it's, first of all, because it's silly, and probably, well, as long as these objects come from different sets, they're very easy to build. And if they're not coming from different sets, I don't even know whether you can build a mosaic, a two-dimensional mosaic of projective planes of order 4. The 21 times 21 matrix, it's tough. So generalizing these to higher dimensions doesn't really make much sense. But for this talk, I think probably the most promising research direction would be these projection cubes of symmetric designs. And now I'm going to stop there. I took a lot of your time. Thanks
for watching, and if there are any questions, please ask. Everybody fall asleep, even the online people. Okay. If there are no questions, then we're going to cut it there.